Hey guys, today we're going to talk about how we can solve for the pH of a weak acid if we are given the Ka and the concentration of that acid. Just like a lot of things that I teach, I've broken it down into a series of steps. So we're going to start with this question. What is the pH of a 1 molar solution of hypochlorous acid if its Ka is 3.5 times 10 to the negative 8th? Well, just like we do in any equilibrium reaction, we want to start by writing our equilibrium expression based on the dissociation of the weak acid. So we're going to start by writing out our dissociation reaction. And I am going to use the simplified version where we don't include water. So I have my hypochlorous acid breaking down into the hydrogen ion and the hypochlorite ion. So my Ka is going to be concentration of the hydrogen multiplied by the concentration of the hypochlorite divided by the concentration of the hypochlorous acid. Now I know that my Ka is 3.5 times 10 to the negative 8th. And I also know that my concentration initially of my hypochlorous acid is 0.1 molar. So we're going to start by making our ICE table. Initially, my hypochlorous acid is at 0.1 molar and these are at 0. So these are going to gain X and this is going to lose X. So at equilibrium, I get that. This is just like what we did last unit. Now, you'll notice that my equilibrium constant for this acid is particularly small. So odds are I am going to be able to ignore the X. What do I mean by that? Well, remember that when we plug this in, we're going to have this on top, right? And normally we would have this on bottom. But we're going to ignore this X because our Ka is so small. We'll come back and test it at the end. So that this will simplify to 3.5 times 10 to the negative 8 is equal to X squared over 0.100. So that if I simplify this, I'm going to get, let's see, I'll multiply both sides by 0.1. So I'll get 3.5 times 10 to the negative 9th is equal to X squared. If I take the square root of both sides, let's see, the square root of 3.5 times 10 to the negative 9th is 5.9 times 10 to the negative 5th. That is a tiny, tiny X, obviously. And what I can do with this now is this is going to be my concentration. I do want to check it to make sure that I'm following the 5% rule. So my 5% rule test is to take that concentration, my X, divided by the initial concentration of the acid, which was 0.1 molar, and then times 100. We're making sure that X divided by my initial concentration times 100 is less than 5%. So 5.9 times 10 to the negative 5th divided by 0.1 times 100 is 0.059. So way less than 5%. Sorry, let me zoom out just a little to make sure you can see all that. Now, this is an acid, so one thing that we're also typically asked to calculate is the pH. So my pH is just going to be, like always, it's the negative log of the hydrogen ion. So in this case, that's going to be the negative log of 5.9 times 10 to the negative fifth, because that was our concentration of our hydrogen. So if I take the negative log of that number, negative log 5.9 times 10 to the negative fifth, I get that my pH is equal to 4.23. And that is how you use the Ka to get to the pH. When you are using a Ka to get to the pH, your X will almost always be your hydrogen concentration. So once you've solved for X, you just take the negative log of that to get your pH. Pretty straightforward. One other thing that we frequently do when we are working with this kind of content is we sometimes actually solve for percent dissociation. So percent dissociation is simply the amount that dissociated divided by the initial concentration times 100. Now, what this actually kind of also looks like is the 5% test. So it does kind of become easy. And one thing that is really interesting about weak acids is the lower their concentration, the more they dissociate. So a higher concentration of a weak acid would dissociate less. A lower concentration will dissociate more. And in part, that's how they reach their equilibrium. So going to that is not too painful of a process. Once again, you're going to start by using an ICE table with the initial concentrations. You're going to solve for X, just like we did in that first problem. And then we're going to remember that X is the concentration of one of our ions. So if we simply take X divided by the initial concentration of the acid times 100, that's our percent dissociation. So let's look at one other problem together. And that problem is this one. Let's do a percent composition, and we're going to do it in two different concentrations to kind of demonstrate this idea that if it's more concentrated, it dissociates less, and if it's less concentrated, it dissociates more. So we'll set up the 1 molar first, and then we'll set up the 0.1 molar. Once again, it's always good news when your Ka is relatively small, because that means you're probably going to be able to ignore the X. So this is acetic acid. My dissociation reaction breaks down into the hydrogen ion and the acetate ion. This is acetic acid. For my first scenario, I've got 1 molar. These are going to gain X. This is going to lose X. I know that my Ka is 1.8 times 10 to the negative fifth. That's going to be equal to my hydrogen concentration times my acetate concentration divided by the concentration of my acetic acid. So when I put those values in, I'm going to have x times x over 1 minus x, but I'm going to ignore this. So ignore me. So when I simplify, I get 1.8 times 10 to the negative fifth is equal to x squared over 1. So x is simply going to be the square root of 1.8 times 10 to the negative fifth. So square root 1.8, 10 to the negative fifth, and I get 4.24 or 4.2, because I only have two sig figs technically, times 10 to the negative third. So in this situation, I've now solved for x, and I want to figure out my percent dissociation. So my percent dissociation is simply going to be my x, so 4.2 times 10 to the negative third, divided by my concentration, which is 1, times 100. So that when I put this in my calculator, 4.2 times 10 to the negative third, divided by 1 times 100 is 0.42% dissociation. So my 1 molar concentration dissociates 0.42%. I could also figure out the pH of this. Remember that X is my hydrogen ion, so my pH is the negative log of 4.2 times 10 to the negative third. So 4.2 times 10 to the negative third. If I take the negative log of that number, I get 2.38. Okay, so let's do the second scenario. In the second scenario, we are, instead of using a 1 molar solution, we're going to be using a 0.1 molar solution. So excuse my taping here just to save a little time. So doing my ICE table for this one, instead of having 1 molar, I'm going to have 0.1 molar. I'm kind of testing the idea that a lower concentration will dissociate more. Once again, these are initially 0, so they're going to gain x. This is going to lose x. So that when I put this into my equilibrium constant, once again, it's just going to be my hydrogen times my acetate divided by my concentration of acetic acid. So that when I plug that in, just simplifying it a little, it's going to be x squared over 0.1 minus x, but we're going to ignore this. By the way, the percent dissociation test is the exact same thing as the 5% test. So as long as my percent dissociation is less than 5, I know that I was okay ignoring that x. So when I simplify this, if I multiply both sides by 0.1, I get 1.8 times 10 to the negative 6 is equal to x squared. So that x is the square root of that. So the square root of 1.8 times 10 to the negative 6 is 1.34 times 10 to the negative third. So if that's my x. So remember that percent dissociation is just how much breaks down, so that would be my x, divided by my concentration, which this time is 0.1 molar, times 100. So when I put that into my calculator, I get that my percent dissociation is 1.34%. And let's also just go ahead for the sake of argument and do the pH. So the pH is going to be the negative log of 1.34 times 10 to the negative third. So the negative log of 1.34 times 10 to the negative third is 2.87. So this acid is 1/10 as strong based on its molarity. But when you actually look at, because slightly more of it dissociates, its pH is not horribly far off of our original one. Let's just contrast. I've got 1.34%. Here I had 0.42%. I've got a pH of 2.87. Here I have a pH of 2.38. So this is a little more acidic, but far less of it dissociated. And so that's one interesting thing about weak acids. The weaker they are, the lower the concentration, the more they dissociate. The higher the concentration, the less they dissociate. Hopefully this was helpful, and hopefully this problem solving isn't too hard after what we did last time. Notice that my percent dissociation was still below that 5% bar, so I don't have to, I can't ignore X. I'm okay. We're going to work on this in class as well. Good luck.